Okay, this is a classic way that the AP Stats exam will ask about probability questions in what is called a two-way table. A two-way table is a way of organizing information. So in this situation, you have a two-way table that organized by gender and whether they have their ears pierced or not. Okay, so the question is, suppose we choose a student at random. Find the probability that, the first question is, that that student actually has pierced ears. Well, if you look at this example here, you look at the total number of students who are in this survey, which is 178, and the number of those students that have pierced ears is 103. So the idea here is the probability of a student having pierced ears would be 103 out of 178. So now let's look at the second question as a male with pierced ears. Okay, so now we're restricting ourselves to just the male role. So in that case, there are 19 males with pierced ears out of a total of 90 males. So the probability of a male with pierced ears would be 19 out of 90. Okay, now the next question is a little bit trickier. Is a male or has pierced ears? So either can be a male or can have pierced ears. Well, if I look here, I see that the total number of males, which we saw here was 90, the total number of people who are pierced ears is 103. So logically you say, oh, 90 plus 103, that's 193 out of a total of 178. And you realize, hey, that's not possible. You can't have more students than our total number of students. You can have 193 students when there was 178 involved. And you realize, oh, we double counted here. We had 19 males who also had pierced ears. So we need to subtract those. So we're going to add the 103, total number of students who are pierced. We're going to add the number of males, but then we're going to subtract all the students that were double counted here. And so I end up with a total of 193 minus 19 is 174 out of 178 students. So there are 174 out of 178 students who were either male or had pierced ears. So this is an example of how to use probability with a two-way table. And usually just simple logic and reading the problem carefully will allow you to solve the problem. So the previous example there illustrates why we can't just use the additional rule when there's overlap. Okay, in this case we had male students who had their ears pierced, and they were in both categories. So that represents the green section of this Venn diagram. That's the people that are in both sections here. So remember, the probability of event A, there were 90 students out of 178. That is the yellow circle, which is this whole region right there. Okay, we also had the students who were pierced ears. They were 103, which would be this whole circle here. And then we had the students who were in both, that section right there, which is 19 out of 78. So if A and B are any two events from some chance process and there's overlap, then the probability of A or B would be the probability of A plus the probability of B minus the intersection, the probability of A and B. So remember, just got to subtract the intersection, just like we did in the previous problem. So Venn diagrams have uses in other branches, so you want to make sure you're using the right vocabulary so that even if it's not a probability situation, people will understand the Venn diagram. So for example, here we use the circle here to represent the event A, and then the outside of it would be everything that's not in event A, which we call the complement of A. So if you notice here, we kind of draw a box around our situation, and the shaded region here would be not A, which is basically not in the circle, it's everything else. Events A and B are mutually exclusive or disjoint. We used this word earlier because they do not have overlap. So if we were to draw two Venn diagrams, we would draw two circles that are not intersecting because there are no outcomes that are in both. And the S represents the sample space, all possible outcomes. In a situation where there is overlap, where there are situations where there are people or events in both outcomes, then we have overlapping circles. And we use the notation A intersect B to represent the overlap, that part of them that is in both circles at the same time, or both events at the same time. If we are looking for the union of A or B, which is sometimes read as A or B, then it's everything, which you notice here, it's the whole green section here. A and B and that intersection. It's all of the three events together. So A intersect B is sometimes read as A and B because it means A and B at the same time. Where A union B is A or B because it doesn't matter whether you're in circle A or circle B, you get counted. So let's go back and look at our two-way table involving gender and Pierce ears and look at what a Venn diagram would look like. So if you notice here, event A, remember there was a total of 90 people. Well, event A is the yellow circle. If you notice, 71 plus 19 is 90. Why did we split it up? Because we had 19 people who were in both circles, who were both male and had pierced ears. So that's the overlap. But you got to note here that 71 plus 19 does have to equal the total here. Likewise, when we look at the pierced ears, we notice that there were a total of 103 people. And if you notice, 84 plus 19 is 103. Again, accounting for that overlap is the 19 here. So, getting used to the notation, A intersect B means A and B at the same time, which is the overlap, 19. A and B complement would be the 71. That would be this section right here. A complement and B at the same time would be this section here, would be 84. And A complement and B complement would be what's left over, which is 4. That's why we draw a box around there to represent all that are left over. Remember, there were 4 people that were neither male or had pierced ears. Conditional probability is an example of a situation where, depending on one event, your probability of another event will be something different a lot of times. A conditional probability is one in which once event A has happened, then the probability of B is then defined. And we use the notation here, using this a line here. We read that as probability of B given that A has happened, or probability of B under the condition that A has happened. I usually read it as probability of B given A has happened. So this symbol here means given that the following event has happened. So here's an example using a two-way table. Okay, event E is going to be the grade that comes from an engineering and physical science course, and event B is the grade is lower than a B. Okay, so some questions that they ask us here, for example, here to find the probability of B of randomly picking a student and they're getting lower than a B. So if I look here, there are 3,656 students out of a total of 10,000 students who got lower than a B. Then the next one asks, so what's the probability of E given that B has happened? So in plain English, that means what's the probability that the student is in an engineering and physical sciences given that they got lower than a B? Well, there we had 800 students out of a total of 3,656 students who got a B or lower. Okay, so there are 800 students in the engineering and physical science school out of a total of 3,656 students who got lower than the B. For the other one, it's the probability of B given that E happens. What's the probability of a student having lower than a B given that they attended the engineering and physical science here? Well, that would be looking at, okay, given that they had a grade lower than a B, which would be 800, out of a total of, we now know that they were in the engineering and physical science college. So it's 800 out of 1,600, which comes out to 50%. So once again, get used to this notation. This means the probability of the first event given that the second event has already happened. And this is the probability, in this case, of getting a grade lower than a B, given that you've already picked a student from the engineering and physical sciences. As long as you read it that way, you can usually reason out these problems. Big concept in probability is trying to show independence. You're trying to show that just because an event happened, the probability of another event has not changed. Okay? So we consider two events independent if the probability of the event happening is exactly the same as the probability of that event happening given that some other event occurred. In symbols, this is the probability of A given the B has to be the same as the probability of A, or probability of B given that A has to be the same as the probability of B. So here's a good example using, again, genders, but now we're using right and left-handed. So the question is, are the events male and left-handed independent? Okay? So if the male and left-handed are independent, then the probability of the left-handed, given that males, that you have a male, has to be exactly the same as getting a left-hander. Okay? So if I look at this, the probability of left-handed, given that male has happened, means I'm looking in the male column, and I'm saying, what's the probability of randomly picking a left-hander from that? So if you notice, there are 3 left-handers out of a total of 23 males. So 3 out of 23, which comes out to be about 0.13 or 13%. The probability of being left-handed overall, now I'm looking at the total column, which is 7 out of 50. Okay, which is 0.14. Notice that these are not equal to one another. Therefore, they are not independent. There definitely seems to be the fact that if you're a male, it changes the probability of being selected as a left-hander. Okay? So if the probabilities are not equal, then they are considered non-independent. Okay, here's a tree diagram. This is a situation we've looked at before, probably getting 2 heads, but a little bit different way of looking at it. Here, if you notice here, here's my tree diagram, heads and tails, the probabilities here, 1/2 and 1/2. And then the second flip, heads and tails, with the corresponding probabilities in both scenarios. But now what we're doing is looking at the probability of 2 heads and saying, aha, this is the pathway that gives me 2 heads. I can get it by using what is called the multiplication principle, by multiplying the 2 branches, 2 probabilities on that branch. In this case, 1/2 times 1/2, and I get 1/4. A little bit different way of looking at it than looking at all the different pathways and saying which one is 2 heads. This will work, especially in situations where the probabilities aren't as nice as 1/2 and 1/2. You just multiply the 2 probabilities together, and that will give you the probability of this one branch, which is what we're looking at, the probability of getting 2 heads. Okay, when you multiply along the branches in the tree, this gives us to the general multiplication rule, and that is that the probability of A and B happening at the same time is the same as the probability of A times the probability of B given that A has happened. And this is, like I said, the general multiplication property, and we're going to see some examples of this coming up. So here's a situation. The Pew Internet and American Life Project found that 93% of teenagers use the internet, and that 55% of online teens have posted a profile on social networking sites. So I'm going to create a tree diagram that represents the situation. So the first event is whether they're online or not. So I make my first branches. Yes, they're online. No, they're not. Well, if you notice here, 93% of the teenagers use the internet. So yes would be 0.93. No would be 1 minus 0.93, so 0.07. So remember, these 2 probabilities have to total 1 if it's truly all the outcomes. Then the second event is, have they posted a profile, say on Facebook or MySpace or any of those kind of networking sites? And it says here, 55% of online teens have posted a profile. So when I make the next tree diagram about an online profile, yes is 55, no would then be 45%. And then to do the branch below, again we have yes and no. But if they have never been on the internet, so then the percentage of students that have posted an online profile would obviously be 0 because they've never been on the internet, so they can't have posted a profile. And so all students who have never been on the internet have not also posted on a profile, so the chances of no would be 1. Remember, that's all students there. So this is how we would complete our tree diagram for the situation. As you can see, the tree diagram works really well here, especially when it's not a heads and tails thing where the probabilities aren't quite as obvious. The tree diagram works extremely well in this scenario. So now the question is, what percentage of teens are online and have posted a profile? Well, if I look here, that's online and posting a profile would be this top branch right here. And I can use the multiplication principle and realize, oh, I can take 0.93, multiply it by the branch 0.55, and that will give me my answer, which is 0.5115, so about 52%. Okay, so this is how we can use a tree diagram to solve problems that are conditional problems like this. Okay, so here's another conditional probability involving internet users, in which they surveyed adult internet users and asked them two questions: how old they were and whether they had used video sharing sites like YouTube. So the survey results came back, and if you notice here, 27% of all adult internet users are between 18 and 29. 30 to 49 is 45%, and people over 50, there's 28% of all adult internet users in that age bracket. From there, they then asked them again if they use YouTube or not, and you can see the different probabilities. 70% of the young adults use the YouTube, 57% of the middle-aged adults use YouTube, and only 26% of the old adults used YouTube. Okay, so we created our tree diagram showing, in this case, there were 3 different branches here because I had 3 different age groups, and then 2 branches each. And you notice that every set of branches always adds up to 1 because it represents all the outcomes. So the questions are, for example, the probability of watching YouTube, given that they're 18 to 29, would be 27%, because it is 0.27 times 0.7, which comes out to be about 18.9%. The probability of using video sharing sites and being in the age 30 to 49 is 0.45 times 0.51, and you can see there about 23%. Okay, so the multiplication principle comes in really handy when you want to find the probability of any one of those branches. You just multiply the tree branches within that one pathway. Okay? Okay, the idea of independence sets up a special multiplication rule that allows us to find the probability of independent events by simply multiplying the probabilities together. So an example of this was the Space Shuttle Challenger, which, if you remember, blew up, okay, because of some failure of O-ring joints. NASA determined that the probability that an individual O-ring joint would function properly was 0.977, so a pretty high percentage that it would actually work properly. Let's assume that O-ring joints succeed or fail independently. What's the probability that all 6 would function properly? Well, probability of the first joint being okay is 0.977. The probability of the second event joint being okay is also 0.977. So all the way out to the 6th one. So what we end up doing is going 0.977 times 0.977, etc., to the 6 times, which is 0.977 to the 6th power, which turns out to be 0.87. So the idea here is that if the events are truly independent, you can just simply multiply the probabilities together to get the probability of combined events. Okay, so what if we want to find the probability of B given that A happens? We have a formula here that we can take the probability of B given that A happens by finding the probability of A and B happening at the same time, which is the intersection of B, and dividing it by the probability of A. So this is a formula that you want to become familiar with and use whenever you want to find a conditional probability of B given that A happens. Basically, you find the intersection and divide it by the probability of A. This works really, really nicely with Venn diagrams. We'll show you how this works in a Venn diagram. So here's an example, okay? We have a situation here where a large apartment complex, they asked them how many of the residents read USA Today and how many of them read the New York Times. And the Venn diagram describes the residents. So it turns out that 35% read the USA Today only, 20% read the New York Times only, and there were 5% that actually read both papers. And so we set up a Venn diagram in which the 5% represents the intersection because they did both events at the same time. And so we wanted to figure out what is the probability that a randomly selected resident who we know reads the USA Today also reads the New York Times. So there's my probability of B given that A happens, okay? So in this case, we want to find the probability of the intersection, which, if you notice here, is 5%. And we're going to divide that by the probability of A, which is the probability of reading the USA Today. But you got to remember, That is the total of this circle. So 35% plus 5% is 40%. So the formula says to take the intersection, which is 5%, and divide it by the probability of A, which is 40%, and this comes out to be about 12.5%. And so this is how you find conditional probabilities in a Venn diagram. You take the intersection and divide it by the total event, whether it be circle A or circle B.